So my lecture today will be devoted to the analysis of linear constitutive law and in perspective to proceed tensor decomposition. Is it right? C'est bon là? Okay.
Can we pull the two hooks out? Yes, please.
Okay. responsible for the coupling will vanish identically in that situation. So if you want to design some sensor, the notion of symmetry is important. So for the notion of anisotropy, it's something you cannot get rid of. If you decide to not consider it, and sometimes you will miss some effects. In other time, you will not capture in your behavior the relevant ingredient for the phenomenon you are interested in. So with nowadays development in material science, this parameter should be taken into account. And maybe, as we will see, if you got study propagation in periodic lattices, you can demonstrate that propagation within periodic lattices is always anisotropic. You cannot have isotropic propagation within a periodic tiling of plane or periodic tiling of space. So studying wave propagation within strain gradient elasticity or within another kind of general continuum is necessarily anisotropic propagation. So you need to take this into account, and you should have information on how this effect can be modeled within your continuum description. This includes the way to write some constitutive laws that will take this parameter into account. Linear law for constitutive behavior, and also floor function to detect if you reach some plasticity flow in an anisotropic continuum. So, as I said before, I keep on working in the big picture of my talk in order to, in a certain way, introduce the big idea at the beginning. Because during that way, when you will see this concept, you will have at least the structure of where we are starting and what is the point we aim to reach. So here I try to represent graphically two things. The microstructure we are interested in, I call it D, and the physical properties that will live on this, over this microstructure. These two concepts are related, and the two have some symmetry. If you take your microstructure here, you can see that if you rotate it by P over 2 rotation, you will obtain the same structure. In the same way, you can observe that you have some mirror in your pattern that will let your microstructure change. The same things can be done also for physical property, but as it is tensor, it's less got less intuition on how things transform or should transform. That is the aim of group representation theory that will be introduced in this talk, and more specifically by the end of this talk. But there are two objects that are connected in some way, possess invariance. So a set of operations will let your geometry invariant, and another set of operations will let your physical property invariant. So the natural question is, how do these two groups are connected? In fact, this connection is summed up into the well-known Curie principle, also known in English literature as the Neumann principle. And this principle states that as soon as you got symmetry in the cause of a phenomenon, you should have the same symmetry into the consequence of your phenomenon. So in terms of group operation, you will have all the elements that let your microstructure invariant, that will let your physical property invariant. But this is not a strict equality, it's just an inclusion, because your physical property can be more symmetrical than your microstructure. One well-known example is if you read some crystallographic book, it will be said that structures that are hexagonal invariant, that are invariant by a six-fold rotation, will produce elasticity that is transverse isotropy. Every rotation, discrete rotation, are contained into the physical symmetry group, which is an infinite one, and it's called transverse isotropy. So there is just a containment relation, and the exploitation of this relation can give you a lot of prior information on your behavior, and using group you can deduce a lot of things without doing any computation. In a certain way, the use of group theory allows you to fly over your topic and to obtain global results. The construction of more specific results is another operation, but before starting your problem, you will obtain some general results about the solution you should obtain. So here is some questions that can be solved without any computation. If I take material that is cubic invariant, I may ask for which one of this behavior, the behavior indeed, is isotropic. Should the cubic invariant material should be isotropic for thermal conduction? Should it be isotropic for electric conduction? What can we say about the piezoelectricity? And the last question is regarding elasticity. In fact, all these questions can be solved directly. And another question that is related is the following. If I got a material, I know this material is isotropic with respect to elasticity. Can I conclude something about its invariance, its isotropy or not isotropy regarding the thermal conduction? So we will introduce different concepts and principles that help solve this question very quickly. Since my talk in this motivation and in the reason I attack this topic was related to generalized elasticity, I will take some time to introduce some concepts. I know that this morning Francesco told us that despite having a lot of different names, all things should be considered as the same. Strain gradient elasticity, Cos-Ra elasticity. It's true in certain way, but there is some small difference between this generalized continuum that should be precised since the beginning. And this precision is kind of very important because in the literature you got a lot of different names for the same thing and sometimes the same name for things that are different. So trying to put some clarity in the discussion, I think it's valuable at some level. So I think the most important distinction in the way on how to extend Cauchy elasticity is the following. You can add to your description you can add to your description information on the higher gradients. In such case, it's the first option. It will be higher grade continua. I will keep as a degree of freedom the displacement field, but I will say, okay, everything is varying kind of very quickly, so the information about the strain is not enough to capture what is going on within the matter. So to capture this effect, I will take another information that will be the gradient of my strain measure. And doing so, I will add gradients in my formulation. The consequence of that choice is to keep the same degree of freedom, as I said, but you will deal with an higher order Lagrangian formulation. You will not be first order, you will be third, second, third, and so on. It's known in physics that higher order Lagrangian are some not well-posed problem. And furthermore, as you extend the order of the associate partial differential equation, you should enhance your description with a higher order boundary condition. I think this is clear from the discussion, the lecture we have this morning. And what is the physical meaning to this higher order boundary condition? It's a question that is still open and not clear in all situations. So that is the first option. The second option is to say, okay, well, I will stay with the first order Lagrangian description of my physical system, but to capture what is going on, I will add more degrees of freedom. This is what is done in the micromorphic elasticity. Micromorphic elasticity, as will be detailed later on, is to add in your description a second order tensor, not necessarily symmetric, in the, as degrees of freedom of your model. So you extend your set of degree of freedom in, but you keep your first order Lagrangian description and your boundary condition remain classical. Okay, so you can make a mix of the two. Also, it's not one or the other. If you want to make a very generalized continuum theory, you can add new degree of freedom and take into account their gradients. You can combine these two approaches. Perhaps
just to comment.
Yeah.
Classical BC, more boundary condition.
More boundary condition, but not higher order one. No, you got boundary condition for your extended.
Additional boundary condition, but the same order.
Same order. Okay, but how do these two approaches relate? That is interesting, and it was investigated by Midley himself in his paper. These two approaches can be connected since we can see either in static or in dynamic behavior that in certain way higher grade continua can be seen as a degenerate cases of higher order continuum. You can put to go from, for example, it's the first, the number one. The number one example is, okay, I'm dealing with micromorphic medium, so I got as a degree of freedom displacement field, and I also have field of second order tensor. And I will have a relative deformation which will measure the difference between the gradient of my first field and the second field, which is the micromorphic field. And if I impose this difference to equal 0, the natural consequence is that my extended degree of freedom will become the second gradient of my displacement field. So if I impose some kinematic condition, I can degenerate one higher order continuum to an higher grade continuum. One reason to choose higher grade continuum toward higher order one is the amount of material parameter to identify is a bit lower. And as we have a lot of parameter, this first approach is a bit easier to handle. The other connection is related to the dynamic behavior. So here what we observe is the dispersion curve. And I don't remember, I think it's material which has hexagonal symmetry due to the Brillouin zone. And we observe the link between the wavelength and the frequency. And when you got a propagation, when a wave can propagate, you will have a dot on your graph. So here we've got two types of branches. Branches that start from 0 and branches with no zero frequency at when the wave is very large. These branches are called acoustic one and are associated to classical degree of freedom. The limit you will see here is the translational degree of freedom of your pattern. Higher other branches called acoustic, here, and higher one are associated to internal degree of freedom and extended, in fact, degrees of freedom. If I will try to reduce my dispersion curve that is computed taking account the full geometry of my pattern, the Cauchy limit will be obtained here when we will have just the usual displacement as degrees of freedom and a linear relationship between a frequency and waves length. So if I try to capture my dynamic features using higher order grade, taking account higher order gradients in my formulation, as I don't had any degrees of freedom, I will lose in the homogenization scheme all the optic branches, and within strain gradient extend a bit the domain that may be described by a continuum description. So we'll have just your acoustic branches, but describe a bit more, and you will be able to see dispersive behavior, since your relation will not be linear anymore. And if I want to get into my equivalent description, homogeneous description, some optical branches, I should take into, I should turn myself to kind of microscopic, a micromorphic description. Without micromorphic description, you will lose all the information about your acoustic branches. So it's a way to put in connection the different generalized continuum you can construct. Here it's an example in one dimension. I think it's very clear. If you got Timoshenko beams, you got 2 degrees of freedom, the displacement and the rotation of your section, and it's a first order theory. And if you put some kinematical constraint, you will obtain Bernoulli beam theory with just 1 degree of freedom and the second and an higher order gradient in your modeling. So the situation can be in some way sum up with this small example. Higher order you got Timoshenko, and if you put some kinematical restriction, you will obtain Bernoulli. The same work also for Reissner-Millin and Kirchhoff law for plates. That is not at all a domain in which I have any expertise. So I think maybe Arthur can make more comment on the connection between this model. So in 3 dimensions, the connection can be summed up within this this graph. If in my higher order description I just add rotation, I obtain cos-rho. And if I made some kinematical constraint on cos-rho, I will obtain something that is not very used. Or maybe I'm wrong, but I think it's not the most famous extended continuum. You will obtain a Coiter continuum. So your rotation in cos-rho will be a strain to follow the second gradient of a certain part of the second gradient of your displacement. And if you add also from cos-rho and Coiter are related to rotational local rotation. And if you also attached other kinematic descriptor, which will be change in volume and change in the orientation of your director, you will obtain something a bit more complex that is the micromorphic theory. And the micromorphic, if you input constraint, will give you a strain gradient theory. Okay, so it's this graph is kind of summary of some, I think, the most well-known higher order elasticity models. They connect in this way. Yeah.
Other names for the same thing.
Mm-hmm.
So cos-rho is sometimes called micropolar.
Yeah.
So if you be a micropolar, it's cos-rho, most of the cases. And Coiter, you find the name couple stress theory. Couple stress theory is in fact
it's sometimes people use couple stress also for cos-rho. It's undeterminate couple stress. That's why I try to choose those names and not to depart from the choice. But couple stress is a bit used for various situations. Okay. So now I will move to the first real part of this talk. I give a look at my okay. So as I'm interested in obtain symmetry classes for constitutive tensor, I'm not focused on one special kind of constitutive law. So I will try to develop the way of proceed in kind of general fashion. So if you want to construct, before, this is very important because what will be said here I think cannot be generalized for any situation. So the basic hypothesis for all this work is we are working in static, I think it will not change a lot if we consider dynamic, but everything will be in regarding into the context of infinitesimal transformation. So no distinction at all will be made between the first placement and the deformation placements. So everything will be seen as vector field over the first placement, indeed. And we're just gonna see things that are connected to linear laws. Maybe some discussion can be made to generalization, but it's not the aim. And this approach is very related to some work that have been made by an Italian researcher called Enzo Tonti, who introduced and we look for analogy between different physical theory and made a classification through a tool called Tonti diagram that can help to sum the relation within a physical theory. So here it's a quick overview at some concepts that are fully developed into the work of Tonti. And you could also find things that are very close in the work of someone called Bernard Nerol, who published on the internet a document that is, I think it was almost retired at this time, and he brought down different things concerning the duality in the structural mechanics. And I don't think he knows Tonti, but the approach is kind of very similar to the one that was introduced by Tonti.
Can you give the reference?
By the end of my talk, all the references are given, so everything is noted.
Send the slides and we publish it.
Yeah. I did not have time to write notes, but I will try to extract from my slide notes on this subject. More easy to read than a collection of slides. Summer work. Okay, so here it will be a very quick things. So it's kind of recipe cookbook on how to construct a linear theory regarding the process of Tonti and Nerol. So in your recipe, the first step is to choose your field theory. What will be the degree of freedom of your concern? As we see before, if I want to make some classical elasticity, I will just take the displacement field. But in the same way, if I want to make some strain gradient elasticity, I will take as my first ingredient just the elastic displacement too. But if I want to enhance my theory, I could take in addition to my displacement field, a field of local rotation coded by tensor field phi. But you could do it with thermoelasticity, adding a scalar field in your theory. And the last example is something that came from gravitational quantum gravity. Some people suffer from too important distortion within as you approach a black hole, so they try to modify the equation of general gravity in that context. And they introduce something that is called a spin-free continuum. Reference are also given. And it's kind of field theory in which your degrees of freedom is described by a field of symmetric second-order tensor. So for us, it's a vector field. For them, it will be a field of second-order symmetric tensor. But the construction, despite being very different from our interest, will be almost the same. And this spin-free continuum, if you look at micromorphic theory and you forget for a while your displacement field as a degree of freedom, you will also obtain something close to what is done in gravitational. Okay. So that's the first level. Choose your degree of freedom. For the second level, there is two ways of consider this this second level. I will say it in choose this presentation. You should choose some primary because I'm much more. I see things by kinematics. People may construct their theory using a statics approach, but I'm much more in kinematics. And you will choose some tensors that will measure how your matter locally is transformed by the action by your physics. In Cauchy continuum, you will add to your degree of freedom a strain gradient, a strain tensor, which is constructed as the symmetric derivation of your displacement field. But if you are interested in strain gradient continuum, your first order descriptor is not enough, and you will add another descriptor of your state of matter locally. And in strain gradient, you will also add the gradient of your strain. In the same way, if you're working with Auffray continuum, you got your degree of freedom, and locally your matter will be its state will be characterized by the strain. As usual, you will have the gradient of your rotation field, and here some relative strains that measure the departure from your classical strain measure to the one you added in your description. Okay, and for the spin-free continuum, you will take as a generalized strain completely symmetric tensor constructed by the gradient of your degree of freedom. Okay, once you got this, in fact, you make a choice for the vector space in which your object will live. And the structure of this vector space are important because for the symmetry classification, it's just the structure of your vector space that will give you the symmetry classes that can be or not encoded by your model. So that's why it's important at this stage to identify in which space your measure are living. And this space are characterized by tensorial order. It's very important. It can be demonstrated that if you don't have a third order tensor as a kinematic descriptor, you cannot see in strain gradient elasticity, you cannot see the hexagonal symmetry. For example, as in Auffray continuum, you don't have any third order tensor in your formulation. Auffray can never see hexagonal symmetry. Everything is settled since you choose your kinematical descriptor. So what I call state tensor spaces are characterized by their order and the index symmetry that define your different elements. So for strain tensor, we are living in this space. So here, when I put parentheses, it means that I can interchange my indices without changing the result. So strain tensor is a tensor that is symmetric between permutation of the two first indices, and strain gradient tensor is symmetric with is the third of the tensor symmetric with respect to permutation of the two first indices, leaving the last one apart. So this construction can be summed up saying the space of strain tensor is the symmetric tensor product of the space I'm working on. If I'm in two-dimensional space, a strain tensor will live in S2 of R2. And if we are in three dimension, it will be the symmetric product of R3. And here, tensor, the space of strain gradient tensor is constructed this way. So, okay, here I got slides that are overwritten, so it's not the more beautiful in my presentation. I will be quickly on that part. Okay, you got the set of degree of freedom you want. And from this set, you build a collection of state tensor space that measure what is behave locally on your matter. Okay, so if I put together all the space involved in my description, for strain gradient it will be this space plus this one, I will obtain what I called E. Big E, this vector space that will describe at each point the state of my matter. So I can imagine that I need n tensors to locally define what is going on each point. Okay, and from this local description into kind of generalize the kinematic approach, I want to associate an energy. So I will try to construct some dual state tensor, which is of a linear form over my space of description, and that will return to me the tensor, a scalar called W, that is in fact my energy. So if I expand using the properties of my direct sum, this energy between S, that is my generalized static description, and my kinematics, I will obtain a kind of general law that will involve all the jointly product in my theory. I will move to one example. I think it's more clear. If I'm in strain gradient elasticity, okay, I got my degree of freedom, and as primary state variable, I will take the strain and the gradient of the strain. So I will have as conjugated variable the classic stress tensor that will be associated to my strain, and an hyperstress tensor that is associated to my strain tensor. So the energy of my system will be written as a scalar product between these two elements added by a scalar product between the extended element. And taking the derivative of this energy with respect to my primary state variable give me the Joule object. That's something that is in certain way sum up with this kind of structure that is the Tonti diagram. The primal complex is what is associated to my primary tensor. That is all my generalized kinematic variable. I choose the space from my degree of freedom, and I choose the space that describes my generalized kinematics. And between these two spaces, you can have a derivation that allow you to start from the degree of freedom to obtain your generalized strain measure. And in opposite, I have the kind of static branches in which I will have here my generalized stress measure and associate to, I can also define some space of generalized forces. The operation D is the derivation that allows you to go from degree of freedom to your generalized strain, and it will traduce the compatibility equation, and the dual of this derivation is the equilibrium equation associated to your model. But anyway, I will just assume a bit. Okay. I will assume a bit. I think it's more clear here. If I make just the primal complex, that's the generalized kinematic, and the dual complex, which is the generalized static, I describe, in fact, the structure of my theory, but it's a kind of canonical, because at this level, since I don't associate a relation from generalized stress to generalized strain, I don't have any behavior that relates the two. So I don't have any behavior, so I don't have any information about the material that will realize this, this behavior. To choose a linear behavior will be to choose a linear relation between your extended kinematical descriptor and your extended static tensor. Okay, that is written here. Oh, I think it's clumsy. Okay, some example related to this graph. If I'm in elasticity, here, in fact, this is how you construct your constitutive tensor space. As you wanna go from the primary to the dual, your tensor space will be constructed as the symmetrical tensor product of the two space you use for your theory. I think it will be clearer in one example. If I consider strain gradient elasticity, I need those two spaces to describe the state of my matter, donc the strain and the stress tensor. So the complete description belongs to this space, which is the direct sum of the two one. And if I look for a linear behavior, this linear behavior will be belonging to the symmetric tensor product of the space used for my description. So here I will have S2 of this space, and I can expand my product. So I know that the linear constitutive tensor space associated to that description will decompose into this one, which is a symmetric tensor space that relates second order tensor to second order tensor. I will have this tensor belonging to that space. A tensor belonging to that space is a tensor that took into entry a third order tensor and give another third order tensor as an output. And I will have some kind of elements that will belong to this space. And this space is a coupling space between first order measure and the second order one. If I look at the different elements related to that construction, I will have a tensor CIGLM, which is symmetric between permutation of the two, and this is first and last, and the interchange of these two sets due to the symmetric tensor product. And I will obtain, in fact, that this tensor C is the classical elasticity tensor that relates, in fact, my Cauchy stress tensor to the strain tensor. The element that will live in S2 TIGK will be a sixth order tensor A, will have also a major symmetry. And the element associated to this space, it's a tensor that is called M, which is symmetric between the interchange of the two first and this and third and fourth and this. And elements that belong to this space are in fact a coupling element of the constitutive laws that couple first order and second order first order and second order phenomenon. M here is responsible for those coupling. Indeed. Okay, I will keep it. So if I get back to this description, here we got two different things. These tensors are related to proper physics. It relates the first order strain to first order stress to first order strain, and this one the second order stress to second order strain. So those are called for me proper tensor. And the other one that mix coupling that mix stress state tensor space are called coupling tensor. Typically, electric conduction is a proper tensor space associated to the heat flux, and the piezoelectricity is a coupling tensor between that, because the spaces are put into connection are of different nature. Okay, so I am almost finished this part. What can be concluded about this description? In fact, I can have information on the structure of any tensor space involved. If I took, here I get back to state tensor. My state tensor will be so the strain or the strain gradient, as it is defined according to index symmetry. My tensor space, its structure is contained between a space of completely symmetric tensor, that is defined here, Sn is the space of tensors that are symmetric with respect to the permutation of any one of its indices. And at the other end, my tensor space is contained into the vector space of a tensor having no symmetry at all, index symmetries at all. So by construction, I can restrict the possibility on my constitutive tensor by using the Tanti diagram and by using the mechanism of construction. I know that any proper constitutive tensor, so tensors that linked the primal and the dual of the same physics, must verify this identity. Arbitrary tensor space cannot model constitutive tensor. You should have some kind of restriction. And structural restriction are given by this formula. And in the same way, if you look that tensor space is using for modeling a coupling phenomenon, those tensor space cannot be anything, and due to the process of construction, must respect some constraints that are also given in this by this formula. Okay. So I will move to the second part, but maybe it's the right time to make a break before the second part. So I will start for the second round of this presentation, and I will move to a bit more physics in this this part. Since the great absence of the first part was the matter, and we will introduce now the matter in order to connect physical property and material symmetry. Okay. So here is the kind of summary of what has been done and 3 questions that anyone have to ask when we are making some physical modeling of behavior. This is important because when we make a model, we try to reproduce, to identify certain effects. So knowing since the beginning what can or cannot be produced by our model is an interesting information. It will be developed more in the last part, but those questions are, okay, I got my model, how many different anisotropic system can be modeled by this approach, and in each one of this anisotropic system, how many parameters do I need to properly set up my model? This also means if we wanna view things from an experimental point of view, how many experiments should I made to identify my parameter? For homogenization, it's less important because you can construct this parameter using numerical procedure. But it also gives you information of your numerical procedure. If at the end of the homogenization schemes you don't obtain the right number of parameters, it should be for you an indication that something went wrong within your procedure. Okay, but to answer this question, that is the number of different systems and the dimension of each one of the system, the first point is to connect in some way microstructure and physical behavior. So this part will be mostly devoted to this connection. And by the end of this part, we will have some nice property that allow us to solve our problem quite quickly, because sometimes you don't need to make any computation. Okay, so I will begin with my specimen. I will call it D, and each point of this domain is located with respect to a frame. Choose the frame you want, but your point will be referred to this frame. So as we will remain in linear and infinitesimal theory, no distinction will be made between deformed and undeformed reference. Everything will be in the initial placement. The thing which is very different between a pure mathematic approach and the setting of continuum mechanics is the notion of a point. In math, a point is just a point in your Euclidean space with nothing, no more information. Here, when we make a model, we choose a characteristic size for our modeling. And the size is dependent of what we are interested in. If you study concrete, the characteristic size of your macrostructure and microstructure will be different as if you study behavior of steel or other kind of material or structure. And in fact, choosing this kind of scale of description implies that under each point of your domain, you will have some information on what is the physics that is encoded at a scale below the one retained for your description. That is what can be summed up as the notion of a material point. You will have your manifold, choose a point, okay, it's just a mat point. But in your modeling, in this point, you will have information on what is contained below. That is what I try to indicate in my figure. For me, material point is mathematical one plus some microscopic information. A reference that is cited here and given in the bibliography is the one from Zhang and Bauer, who investigate a lot those different notions within the 90s. And some of the things that are said in this part are coming from paper of Zhang and Bauer. So what is hidden under material points? But it can be a lot of things. If you study metal at a certain scale, you will lose information about your microstructure. If you model the wood, you will have also microstructures that will be contained in your material point, and so on for all the different situations that you will have to deal with in your modeling approach. Things are very different. We are not just dealing with kind of crystalline structure. We may have a very different amount of microstructure. And as for crystal, this microstructure can have some invariant property with respect to some transformation. So what we are going to do is to define this invariance property. And to that aim, we will make some short digression on group theory, just in order to give the important notions that we should handle. So here I just remember what are the axioms of a group. Here the definition is given for a set of discrete elements, but in practice we will move to a continuous group of transformation. But the idea is strictly the same. So if you consider a finite and discrete group called G, and G will be the name in the following, it is a set of elements with also an operation that allow to compose those different elements. And what makes this set together with that operation a group is the fact that you got the closure. It's the third point, but I will begin by this point. The closure means that if you take two elements and make the product of those two elements, the result will also belong to your set. Any combination of elements taken within your set gives you, as a result, an element in your set. That is the first point. The second point is you got an element which is neutral. This element is here, and if you compose this element with any other element in your set, you will obtain at the end the element you enter in your product. So it's the identity element, and this element is unique. And the last point is for any element, the fact that you got an inverse operation. That means you take two elements, one is the inverse of the other, and the product will be the identity. And any element you can take will have in your set is inverse. And group is in fact, with all this three property, it's the language of symmetry. Here I give one simple example. This simple example, we will get back a bit later on this one, but here I will present it quickly. It's called D3. D is a dihedral group, and it's a group of operations that contain two types of elements. A dihedral means that you will have in your set of operation rotation and mirror. The rotation are illustrated on the first line, and the mirror are illustrated on the second line. And as you see, these elements are the elements that take one equilateral triangle and let him invariant. Let's take my triangle ABC. If I make a rotation by 2p over 3, it will transform my triangle into a new configuration that cannot be distinguished from the initial one. But I can keep on and make another rotation. So the composition of two rotation is another rotation within the group that will let also my figure invariant. And aside of this rotation, as can be observed here, I've got some mirror operation taking my triangle, if I flip B and C, I will obtain at the end the same triangle. And so you can count the different symmetry operation in this group, and you will at the end observe that you will have 6 elements. So dihedral, I will get back later, is the union of cyclic rotation, cyclic operation, I mean just rotation, and mirror. That's the 2 elements that are contained in. One exercise that you can do, that I will not, it will take too much time, but it's kind of interesting, is to make a table with all the operation on the row, whole operation on column, and make the product of all your operation taken 2 by 2. And you will observe at the end that you will observe 2 things. You will observe that your structure is closed, because any combination will give you another element, and you will discover during this table that the order of the operation, and the order in which you proceed your operation is important. This kind of group is called non-commutative, because if you take one rotation plus a mirror, will not give you the same structure as a mirror followed by a rotation. It can be observed in your table, because at the end of your product table will not be symmetric. So your group is not commutative. Well, there is a lot of things that can be said on group structure, but I think it's not the aim today. But it's very interesting to play with this different rule to have some feeling. What is more interesting for us, more generalization that is interesting, is to go from discrete rotation, discrete transformation, to a continuous group of transformation. I mean by continuous group of transformation, something that is often called a matrix group. And for us, it's the information which is relevant. For a mathematician, it will be a not good definition, a bit complex between what is continuous and compact and so on. But for us, the way we make the transformation is usually using matrix. So it's a way to imagine this operation. So here I will list some group and give some information about their meaning. As usual, you got in group and other thing, you got something general, and after you put some restriction to obtain transformations that are more specific. In our case, the more general group that can be used is something which is called GLD. GL is the general linear group. It's a group of matrix. If we are in D dimension, it will be a square D matrix, with the only restriction to define a non-singular transformation. Non-singular transformation simply means that the determinant of your transformation is not equal 0. And that is important because as the axiom of group, in the axiom of group, you have that your operations should be invertible. The condition Q not equal 0 ensure you that you can have a transformation that will be invertible. Okay, and you can check the other property. Two invertible transformation give an invertible transformation. And for the identity, but just take the identity matrix, it will not change anything. So it's quite easy to check. And in an example here is for in continuum mechanics, homogeneous transformation are encoded by the group, the general linear group. Okay, so here for GL we just ask the transformation to be non-singular, but we can impose other, further restriction. One further restriction can be to set the determinant equal to 1. In such case, the meaning is you wanna preserve the volume within your transformation. And this new group is called the spatial linear group. It's the group of invertible transformation that preserve the volume. It's the group of isochorous homogeneous deformation, or the symmetry group of incompressible fluid also. But it's not the way, it's not the transformation that interests us today. Because for us the symmetry is not to deform the matter and to see at the end if we obtain the same things. For us it will must more be today what will be rotation and mirror, all the transformation that not deform the matter. So there are two groups, in fact there are one big group and one subgroup as usual of transformations that preserve the distance. The big group is called OD and it's the orthogonal group in D dimension, and it's the group of orthogonal transformation. One classical characterization is that the transpose of your matrix is equal to the inverse of your matrix. Once again, you can check easily that satisfy all the axioms. But more important is, okay, it's the group we are interested in. But what is the information that is contained in this group? The information contained in the orthogonal group is you have the transformation, you have the rotation. You take your object and just turn it around. And just turning your object around, you don't reverse direction, and so you don't have transformation having a determinant equal to -1. Your orientation is preserved by doing some rotation. And this is the definition of the spatial orthogonal group, which among all the orthogonal transformation also preserve the orientation of your frame, of a frame attached to the matter. Okay, and so I got in OD the rotation completed by mirror operation. In mirror operation, you inverse. If you look at frame into the mirror, you will be your orientation will be reversed. Something important, because it can make some trouble sometimes. Usually, people say that in O3, so the orthogonal group in the 3 dimension, the element in orthogonal group that is not in the group of rotation, it's the inversion. Okay, it is true that in O3 the inversion is a non-proper operation. By non-proper I mean that it reverses the orientation, but it depends on the dimension. That's why here I speak about mirror operation that are improper in any dimension, but inversion are improper in odd dimension. Take the trace of your operation, it will be -1. But if your space dimension is even, inversion is keep the determinant equal to 1. So in 2 dimension, O2, the inversion preserve the orientation, but not in O3. So that's a kind of tricky point. that you can find some problem, some paper writing to that to this point. Even other dimension space and other dimension space should be distinguished sometimes. Okay. So now I introduced the vocabulary of group, and I want to use it to characterize what is contained in a point below a material point. And okay, what will be the symmetry group of MP? MP is my microstructure under P. It will be the set of all operation I will take into the big bag of orthogonal transformation. Into this big bag, I will keep all the operations that will let the point of my microstructure invariant. So, okay, I got a rotation. Okay, I keep the rotation. I got a mirror. Perfect. I keep the mirror. So you make a set, which is a subset of your group, orthogonal group, and much more of just being a subset. It will preserve the group structure. So your symmetry group is a subgroup of the set of all your transformation. Okay, but the point, which is very important, is that a group is relative to an orientation. Here, I got the same. So the question is always, when I say the same, what you mean by the same? If you don't give a definition to the same, a lot of people in a room may or not agree on the ideas that things are the same or not. So here, is the structure at P the same at Q? For some, we will say, okay, if I rotate, it's the same, so the structure is the same. But some other who will accept another definition will say, okay, I take the structure and I translate the structure to put on Q. The two structures don't superpose, so it's not the same. So always, you should always define what the same mean for you. And for symmetry group, and that will be all the difference with the symmetry classes, group is relative to an orientation. So here, the two microstructures are just rotated one from the other. Okay, the group are not the same. So if I take the intersection of these two group of symmetry, I think that the identity is just the only element in common. So this sentence is bold, is really important. Notionless group is relative to an orientation. And you cannot compare with group what is, well, with group. You cannot directly compare two groups of two points taken separately. That is something that very often is forget. When we're speaking about material, we will say the material is orthotropic. Okay, but it's the type of symmetry, it's not the group of symmetry you gave me as an information when you said the material is orthotropic. For example, what is not the same here? It's here the mirror operation is oriented that way, and here the mirror operation is oriented this way. So the two mirror operations are not identical. So one quick, I think it's not very important, but one quick remark is, okay, in continuum description, as I said before, the exact description of your microstructure is lost. And you keep some information, remaining information on your material point. How precisely things are organized at the material P, you don't know. But you know at upper level the symmetry group that is contained below your point. And you can have some value also, but the geometry in some way is lost in your modeling process. So if you only consider that under the definition of material point you got a symmetry group, material point is the information above any point. I said the material is heterogeneous in this case. If your material is heterogeneous, over each point of your manifold in your domain, you will have as an information the symmetry group of the matter. And this symmetry group that live over any point of your domain may change. There is no notion of, for general heterogeneous material, there is no specific notion of continuity between one group on one point and one group on other point. So for heterogeneous material, you can speak only of the symmetry group at a particular point. There is no notion of global symmetry group. It's a local information only. And if you move to homogeneous material, the definition which was given here for the point P become true for any point, so we just cut P into this definition. But in general, this definition is just local. Well, there is something that's not very important here. Okay, so I introduce a group of symmetry and warn you not to do undue comparison. But the question is, okay, so if group is not the right notion, what is the right notion to speak about the type of symmetry? So how to compare objects with different orientation? This notion will be very important, much more for physical behavior than for material behavior. But as we saw it now, I introduce it now. Okay, how can we express that the group over the material point P is the same as the symmetry group over the material point Q? In fact, it's kind of natural. If I said this, it is the same, you want to say, okay, it is the same modulo the action of a rotation. And it is this notion of, if I made a rotation, I can put my microstructure and put it in the same position as what is the microstructure in point P that allow you to compare different group. And it's the notion of symmetry classes. You will have for 2 points with symmetry group, these two groups are of the same type if they are conjugate. Look, the conjugation is the fact to left multiply by G and right multiply by the transpose of G. And it means that you turn all the elements, your symmetry element. If you can find in all the transformation an operation that will take your group to put into orientation, the same orientation of another group, okay, you can say that the two microstructure have the same, belong to the same class of symmetry. And what is interesting, it's to be in the same class of symmetry is an equivalence relation. So it means that you must be into one class of symmetry, you cannot be in two classes of symmetry, and you can classify all your symmetry group into different type. Okay, and the other information is, for example, if I work in the 2 dimension, I know that the symmetry classes that will be allowed are necessarily conjugate to one subgroup of O2. And the same if I work in 3 dimensions. All the allowed class of symmetry are indexed by the subgroup of the general group of transformation. So it allows me in the next slide to introduce the subgroup of O2 and the subgroup of SO3. I can do the same for the subgroup of O3, but it's a bit more complex and lengthy to introduce the subgroup of O3. And you can find this information in any crystallographic teaching book. So I will not spend too much time on the subgroup of O3. Okay. So I will just begin in 2 dimensions, and after I will add what can happen as a subgroup of 3-dimensional relation. In fact, when we saw the triangle, we mostly do all the job, because there is not a lot of possibility as a subgroup of O2. What can be your subgroup? Okay, one, the identity. It's the trivial subgroup. You just have one element. It's the identity element. Nothing happened. After, you got ZK and DK. The other can be constructed from those 2 Ks. ZK, it will be a group of operation. It's called the cyclic group of operation. I did not it here using D, but you can, I don't remember the name of the crystallographic system. I think it's Chanflies or anyone. It's sometimes used using the letter C. Look, in some publication you will see C, and here I use D. It's the same idea. Okay, it's a cyclic group that contains only rotation. It's in fact generated by the rotation of angle 2p over k. So if I take Z2, the rotation that is contained is 2p over 2. So Z2 contains the p rotation. And you make 2 product of p rotation, you make a complete rotation, and you got your identity element. If I look at the rotation of a triangle, the rotation that let my triangle invariant are Z3. No mirror at the time, just rotation. That 3 is the group generated by 2p over 3 rotation. And if I compose 2p over 3 times, I will obtain the identity. So in cyclic group, it's just rotation, and you got a k different elements. So in Z3 you got 3 elements, in Z4 you got 4 elements, and so on. Okay, physically what it means. Physically, in Z you just have rotation, you don't have mirror. So Z is the symmetry classes that will let a chiral figure invariant. Here it's an example of Z3 figure. The only symmetry operation are rotation by 2p over 3. Okay, so this figure can exist oriented that way and can exist oriented the other way. Since you don't have any mirror, you have 2 kinds of possible chirality for your element. So looking for Z invariant physics or Z invariant microstructure is looking for Z invariant. Because structure being in ZK classes are chiral. And okay, and if I go now adding mirror, I go to cyclic to dihedral. Dihedral is just what you got before adding your mirror. Here it's Z3. Okay, I will add some mirror here, 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 and I will obtain a figure that is invariant by rotation as before, but which is also invariant by imposing some mirror operation. So from Zk I construct Dk, and since you got mirror operations that let your structure, your object invariant, it's the classes of a chiral pattern. If something is D something invariant, this object, be it a microstructure or a tensor, is non-chiral. Okay. So the remaining one is SO2. SO2, okay, I push my level of rotational invariance to infinity, and I got something which is invariant by an infinitesimal angle of rotation, but which do not have any mirror operation. That's kind of weird, because in 2 dimensions, how can you be infinitely invariant by rotation without having any mirror? So the answer is kind of simple. Something which is SO2 invariant will be a kind of cycle, but with if I have something that is imagine a car that is racing over my loop in one direction. I got an infinite order of symmetry, but the orientation you introduce on your circuit make it SO2 invariant and not O2 invariant, in which case you lost information about your orientation. You can also see it if you attach some pseudo vector to your cycle. If I attach the pseudo vector and I make a mirror operation, my vector will change sign. Our last example is also a cone. It's you got invariant. You're infinitely invariant in rotation, but you don't have any invariance you don't have any mirror. Here, the equivalent will be a cylinder. Cylinder got an infinite axe of rotation and infinite number of mirror. Okay, and Z2, the second one is you don't have rotation, you just have one mirror. But if you got Zk and Dk, you got everything you want, just can deduce everything. Okay, that's 4 subgroup. Yeah.
I think that you should add some X in Dk. What you call Dk. If you make the difference between groups and classes clear, you should add some X in your definition.
Some X?
Because Dk is an X to it. On the axis. The axis you choose.
Oh, yeah. No. Okay.
Because Dk is a class, and Dkx.
That's totally true. Here, if I want to precise, that is the way that, okay, that's why I precise in Z2 sigma x the choice of my mirror. And I can always modulo one rotation, put it in coincidence. Yes, that's perfectly true. In its own, it's kind of meaningless. You should give an axis. Okay. So here it's what happened in 2 dimensions. Now I can extend it a bit, and here axis should also be specified, reference axis should also be specified. I can extend it, this notion of subgroup, to one bigger dimension. If I extend dimension, I will keep the result of my former dimension and add a new object. Here I move from O2 to SO3. So okay, I keep what I show you for SO2, and I will add some new figure, and these new figure are specific to the third dimension. And it's indeed the symmetry group, but modulo one rotation, you can put group in concordance, are the symmetries that let the Platonician solids invariant. Platonician solids are the only are the equivalent in 3 dimensions to regular polygon. In 2 dimensions, you got an infinite number of regular polygon, and if you go to 3 dimension, you just add 3 or 5 regular polygon. And if you go to a higher dimension, it will appear that I don't know if it's from 5 or higher. Each time you just add 3 a new generalized regular polygon. So the number is dependent of the dimension. But in 3 dimension, it's the Platonician solids that are here, the tetrahedron. You got 12 rotations that preserve the tetrahedron. You got also 2 other solids called the octahedron and the cube, and indeed their symmetry classes are identical. For they are dual in certain sense, and they are left invariant by 24 rotation. So cube and octahedron all came from octahedron. And if you increase the level of symmetry, you will obtain the icosahedron and the dodecahedron, who once again are dual one with the other. So the same symmetry elements. And this figure are preserved by, I think it's 60 different rotations. Okay. And, okay, but you got the jump. If you have what is more symmetrical than an icosahedron, it's a sphere. You cannot construct something in 3D that have more symmetry than an icosahedron. It's just for rotation. But if you took inversion, okay, you will add the inversion operation, but if you push forward, you will make a jump from discrete to automatically continuous symmetry. You cannot approach continuous symmetry like in 2 dimensions by increasing the number of symmetry. This beyond icosahedron, you just have the sphere. Okay, so it's the subgroup of SO3, and that for 3-dimensional even-ordered tensor, that's just what interests us. For all 3, it's constructed from everything we just see and taking special product with inversion. In fact, O3 is the semi-direct product of SO3 and the inversion. So if you got that, you can construct all the rest. So that means that any physical and material object must be of one of the type just introduced before, but no other possibility. Okay. So, okay, so I just discussed up to now about material, and now I will discuss about physical properties, and in a second movement connect them. So also here, okay. Here my hypothesis is I will model tensor using the procedure I just discussed in the first lecture, and my tensor will be of a finite order. I have no other precision. So I got some finite order tensor generated from a constitutive tensor space, doing some symmetric tensor product and tensor product. If our material is heterogeneous, we got tensor over each one point of my domain. So my physical property should be referred to one special one special point, and the symmetry may vary from one point to the other. And if I am homogeneous, I can get rid of this specification and saying and representing my field of tensorial property just by one element. So we will stay in homogeneous case. Okay, so here I try to forget the matter now and try to picture over the point P and Q some specific orientation for the property under interest. So we can see that over P I got strong directivity toward that direction and a small towards the orthogonal one, and things are different over Q. So the question is, okay, I got a tensor. How do this tensor over a point or anyway transform if I made a rotation acting on him? How do I turn a tensor? Physically, I turn the matter and the tensor will turn. But in the abstract way of mathematics, you can take a tensor and define the action of a group of transformation on this element. And that was it explained here. I take my tensor, got n different legs, and I say I will make G out of OG act on T. How do G act? That he will act on each leg separately. If I got a third tensor, I got G, G, and G acting on T. You got as many G elements as you got legs on your tensor. Okay, so as I know how to turn a tensor, how to transform a tensor, I can define how the symmetry goes of my tensor, and the definition is rather simple. Okay, I take element in my group, and the element of my symmetry group will be all the elements in such a way that the transformed tensor is not cannot be distinguished from the original one. So G star T equal T. And once again, same causes, same consequences. In the notion of a physical symmetry group, the physical group is related to an orientation. We saw it with material symmetry, so it's kind of natural now to take this to make this distinction. So in the same way, I hasten here a bit. Since I want to compare physical tensor in different orientation, I should discuss about physical symmetry classes, and it's strictly the same idea. with here a stupidity written on my slide, because it's not the G star product, but as before, what should be read is GT2, because what I transform is a group and it's not a tensor. In the same way, if I want to compare two tensors in different orientation, I have to compare their group of symmetry. If the group of symmetry can be put in concordance using one rotation, I will say that these two tensors, not necessarily the same tensor, but they are in the same symmetry classes. In same symmetry classes, you can have different tensors, but the type of symmetries will be the same. And since it's an equivalence relation, you can assign to any tensor its type of symmetry with this operation. And as before, since the group action is OD, the type of symmetry you can have must be conjugate to a subgroup of the full orthogonal group. So that means that with no regard to the tensorial order, if you are in O3, SO3, you can be conjugated to one of the subgroup of SO3. Yeah?
I'm also...
Yeah, you're a bit hidden by the...
I think it's not true that any tensor has a symmetry group in the strict sense. It may only be a half group. May only be a half group. You can construct tensors where we have non-invertible non-invertible matrices which we apply to the tensor and still use the same tensor.
You can make some G which is not invertible? Yeah. Okay, but it's another definition, maybe related to another problematic. But if G is not invertible, it's not a group operation. Because you cannot inverse your G.
That means not a group, it's just a half group.
Oh, okay. I don't know the notion of half group.
Maybe semi-group.
Okay. I don't know the use of semi-group in that context, but it might be an interesting discussion. Okay. Okay, so the next step is, since I know that any tensor regarding its symmetric group can be put in concordance with one subgroup of the group of transformation, that means give me a tensor and I can put in this this class or this other class, the consequence is that you can make what is called the isotropic stratification. That is, you take all the tensors in your vector space and split them into sets having the same kind of symmetry. This stratification can always be done and is abstractly represented here. The space of my behavior will be decomposed in all the tensor having H0 as class, plus all the tensor having H1 as class, etc., until all the tensor having HP as class. Here I put them in increasing order of symmetry. So TH0 will be the set of tensor with the lower level of symmetry. Here it will be the set of tensor having the greatest level of symmetry. This decomposition is called isotropic, and here is the stratum of elements having H0 as a class of symmetry. So before giving some example, Well, I will just say two things. In our case, P is always finite. You always have a finite number of symmetric classes. And H0 is not necessarily the identity. For example, if you take the symmetric matrix that can model the thermic conduction, you can diagonalize your matrix, and in your diagonal form you can permute all your eigenvalue. So all this permutation of eigenvalue show that the symmetry classes of a second order symmetric tensor, the most general second order symmetric tensor, is the D2 symmetric classes. If you take a vector, the most general vector is always invariant around himself. So for a vector, the least symmetric classes is O2 according to rotation, and the most symmetric classes is the null vector, so it's free. So here is some decomposition, some stratification. For conductivity tensor, okay, the idea is very simple for second order symmetric tensor. I take a second order symmetric, I can diagonalize, compute its eigenvalue. So three possibility, each eigenvalue is different, so your D2 invariant, you're in the classes in class G2, it's orthotropic. Either you got two identical eigenvalue, so you are transverse isotropic, or you are three identical value and you are isotropic. Here I just consider the action of 3D rotation. And here it's the same thing, the same stratification for the elasticity tensor. As a result, from the first part of my lecture, we know that the elasticity tensor can be constructed as S2, the symmetric product of S2 of R3. I take the space of straight tensor, and I take the symmetric product due to the hyperelasticity. So a non-trivial result obtained by Fortin-Gianello in 1996 is that this space can be decomposed, and decomposed exactly into 8 strata. Here it's the triclinic one, monoclinic one, orthotropic, trigonal, tetragonal, isotropic, cubic, and transverse isotropic, and isotropic. Well, I should say the amitropic, but it's not real use. And here I also give the same structural decomposition in 2 dimensions. So we're going to compute tomorrow explicitly this decomposition. And so we can see that going from 3 dimension to 2 dimension, the symmetry classes are rather different. We've got 8 classes in 3 dimension with a trivial symmetry classes, and in 2 dimension we just have 4 symmetry classes, and the least symmetric one always have invariant property. And what is more important, indeed, here it's not vector space. It's not very complicated to see that stratum are not vector space, because you make in the same set objects that are transverse isotropic frame. You can have 2 objects that are transverse isotropic with respect to different axes. So if I make the sum of one with the other, the result will not be transverse isotropic. So the isotropic stratification is not decomposition into vector space. Those elements are not vector space, because you can have elements with different orientations. So to make the sum, you will destroy the symmetry of your element. Okay, so I will finish within 5 slides and keep the last part for tomorrow. So now I will begin to make connection with the different concepts I just introduced. So, okay, now I get back to my Curie principle. I already told you something about, and okay, the symmetry element of my physical property should be the symmetry element that lets my physical, my microstructure invariant should let also my physical property invariant. So here, since I got that D4, in fact, to speak in language of group, the symmetry classes here is D4. We can see that the physical property I tried to graphically represent is also D4 invariant. But it can be more symmetrical. But, okay, remark and consequence. The orientation matter, I already spent time. But you can have, if you compose your structure, your material with a lot of different material, you can have some non-trivial example. I can build a geometry having no material symmetry, and at the end obtain a behavior that is completely isotropic. Sometime I will say, okay, I got hexagonal lattices, it implies that my elasticity is transverse isotropic. This trick is almost is well known, but you can choose to cut, to destroy your material symmetry, keeping your physical symmetry very high. Here it's an interesting example. Extract from a PhD in Nantes. The student built a periodic lattice of Timoshenko beams. So here you can make the translation to obtain your complete lattice. And your Timoshenko beam is defined by different beam having the material parameter different, and if you choose carefully the different parameter of your beam, you will produce at the end. You can produce at the end an isotropic behavior. So your physical property is very symmetrical, but your material symmetry is very low. So you can produce some very counterintuitive effect playing on that trick. If this building brick was made of only one material, I should not produce this effect. But if you begin to play with different material, you can do something interesting. Okay. I checked the computation because the first time you see something with no symmetry implying something with high level symmetry, it's a bit tricky. So it's a kind of exercise. Which one are included in the other, and which are not included in the other. So for my first cases, my material is invariant by D4, and my physical property is also invariant by D4. So the inclusion in that case is true. So everything is well. So I can have an orthotropic behavior on an orthotropic structure. That's what is the meaning of the first case. Here, can I have trigonal tensor symmetry over a tetragonal lattice? It's not possible. The inclusion is not true in the second case. In the third case, my matter is also a tetragonal D4, and my physical property has an infinite order symmetry. So the inclusion is true for this combination. Is true for the third column. For the fourth column, my matter is invariant by D2, and my physical property is invariant by D4. Okay, that's function. You can have your physical property is more symmetrical than your matter, but any operation that lets your matter invariant lets your physical property invariant, so no problem. But the converse is wrong. If your matter is D4 invariant, your property here it's just D2 invariant. That's not working. We don't have inclusion in that case. And for this one, the inclusion is also trivial. So it's just a little and a small game. The idea is you can have different things for matter and for physical symmetry, provided they are connected, but you may have something very different. Okay, and to conclude this talk, I will close it with the Hermann theorem, which is rather simple also to demonstrate, and very useful in practice because it gives you results without making any computation in some case. It's kind of miraculous result because it will link the order of your rotation. Okay, a square is invariant by order 4 because you make 4 rotations before reaching the identity. So it connects the order of your rotation with the number of legs your tensor have. And what is contained in the first theorem, the other just a corollary. If you have more rotation than legs to your tensor, you must be at least transverse isotropic. That's what's stands for elasticity. Elasticity is a 4 legs tensor, and if I consider a honeycomb, the honeycomb structure is invariant by an axe of rotation of order 6. 6 is greater than the number of legs of my tensor. I'm at least transverse isotropic. That's all you to have a direct and a quick answer to many problems. And okay, and if you have more rotation than legs plus mirror, okay, so you are at least transverse isotropic. Here it's anitropic because you don't have mirror, and here is isotropic because you have mirror. Okay. That seems a bit trivial, but you can deduce a lot of things without making any computation. One classical example, I know people make the computation, but it's useless. You can ask yourself, give me one quasi-crystal, like got a Nobel Prize in 211 for the discovery of quasi-crystal, which are made of quasi-hadron structure in some way. Is elasticity isotropic or not for icosahedral classes. You can make computation or using in a good way the Hammond theorem to conclude in two lines. The first line is, okay, icosahedron contain 5-fold of symmetry. Okay, if I choose one plane, 5 is greater than 4, so I'm sure that in at least one plane I'm transverse isotropic. Okay, you know you are transverse isotropic in one plane. But how many planes of symmetry do you have in the icosahedron? You got a lot of planes of symmetry. So if you are isotropic in one plane of symmetry and by spatial transformation, you know that you are transverse isotropic in another plane of symmetry. The only figure that is transverse isotropic in two different planes is the sphere. So by knowing the result in one plane and looking at the Platonician solids, you conclude, without making any computation, that you must be isotropic for icosahedral symmetry. No computation. And if you try to make act on your tensor all the generator of the icosahedral class, take your 21 coefficient and make all the rotation to kill your coefficients, it will take you a lot of time using formal computation to arrive at the same result. With a little bit of geometry, it's solved in one line. So that's why I do love Hammond theorem. And another consequence is interesting. Strain gradient elasticity is defined by a 6th order tensor. Okay, so for an hexagonal tiling like honeycomb structure, we know without making any computation that strain gradient elasticity may be anisotropic for hexagonal structure. And in fact, adding some result I don't tell you today, it's not a possibility, it's an obligation to be anisotropic for hexagonal elasticity without making any computation. So I think it's kind of using group is sometimes very beautiful way to have a global structure very quickly. So the program of tomorrow is to give a closer look on all that more precisely and study anisotropy. Today we just say when we have isotropy. Tomorrow we're going to classify anisotropy. So that's the end for today. Thanks a lot for your patience.